Good morning. We are now discussing the relation between the elastic constants Q, K, eta and sigma. In order to derive this, I consider a cube of unit side of 1 unit length, and the cube is ABCD EFGH is the cube having each side of 1 unit length, and the side EF is along x-axis. You can see here the side ED is along y-axis and the side EH is along z-axis. Also, let P is the force acting along x-axis, Q is the force acting along y-axis, and R is the force acting along z-axis. We have two P's, two Q's and two R's acting on the opposite faces along x-axis, y-axis, z-axis, and all these forces are acting in the outward direction and they are perpendicular to the surfaces of the cube. Since the force is acting along x-axis, it produces elongation along x-axis, because of which the cube on the other two sides gets contracted. It gets elongated along x-axis and gets contracted along y-axis, along y direction and also along z direction. Since before the application of the forces, the side of cube is of unit length, the elongation along one direction and contraction along two directions changes the shape of the solid cube that we have considered. And along x-axis, the elongation is longitudinal strain that is given by alpha. And along the two directions, y and z axis, it gets contracted, because of which the lateral strain is given by beta. Therefore, the stress is P. Now let Q is the Young's modulus of the material of the cube, and if sigma is its Poisson's ratio, then Q is equal to P by alpha, or simplifying this we get alpha equals P by Q, and sigma equals beta by alpha, lateral strain by longitudinal strain, or beta equals sigma into alpha, or beta is equal to P by Q into sigma, since alpha is P by Q. Now, hence, the elongation produced by P along x-axis is P by Q. P by Q is the elongation produced along x direction, and the contractions produced along y and z directions are sigma into P by Q and sigma into P by Q. The lateral contractions along y and z directions being the same. Similarly, the force Q acting along y-axis produces an elongation of Q by Q, where capital Q is the force and small q is the Young's modulus, and lateral strain produced along z-axis and x-axis respectively are sigma into Q by Q and sigma into Q by Q. Again, they are same. Similarly, longitudinal elongation or longitudinal strain, or in other words, the elongation produced along z-axis due to the force capital R is this is R by Q, not Q by Q. This is R by Q, and the lateral contractions along x and y axis are sigma R by Q and sigma R by Q. Therefore, the net elongation along x-axis is P by Q minus sigma Q by Q minus sigma R by Q. Similarly, net elongation along y-axis is Q by Q minus sigma P by Q minus sigma R by Q, and net elongation along z-axis is R by Q minus sigma P by Q minus sigma Q by Q. So these are the net elongations along along x-axis, y-axis, z-axis respectively due to the application of the forces P, Q, R along x, y, z-axis respectively. If these forces are equal, if P equals Q equals R, then net elongation along x-axis is P by Q minus sigma P by Q minus sigma P by Q, or that becomes P by Q into 1 minus 2 sigma. Similarly, the net elongation along y-axis and z-axis will also be the same because P equals Q equals R. Hence, the new volume of the cube is given by the expression, it is the original volume plus the increase in volume. Therefore, new volume is, it is 1 plus P into 1 minus 2 sigma by Q whole cube, or that is P, or that is equal to 1 plus 3P into 1 minus 2 sigma by Q. And we have neglected the higher powers because sigma is small. Since sigma is small, we have neglected the higher powers of P or the higher powers of sigma. Hence, the original volume of the cube, this is the original volume and this is the increase in volume of the cube. Therefore, increase in volume is 3P into 1 minus 2 sigma by Q. Therefore, the bulk modulus K will be equal to P divided by the increase in volume. It is 3P into 1 minus 2 sigma by Q, force by increase in volume. Or K is therefore equal to Q by 3 into 1 minus 2 sigma. And if P equals minus Q and R is equal to 0, then there will be a net elongation of P by Q plus sigma P by Q, that is equal to P into 1 plus sigma by Q along x-axis when P is equal to minus Q and R is equal to 0. If there is no net force acting along, if there is no force acting along the direction, and if the magnitude of P is equal to magnitude of Q with a negative sign, or in other words, if P equals minus Q, then this will be the net elongation along x-axis. Similarly, the net contraction is P by Q into P by Q plus sigma into P by Q, that is 1 plus sigma by Q along y-axis. This is the net elongation along x-axis, this is the net contraction along y-axis. As the elongation in one direction is equal to the contraction in the perpendicular direction, therefore the equivalent shearing strain is given by, the equivalent shearing strain is theta equals 1 plus P sigma by Q plus 1 plus P into 1 plus sigma by Q. The elongation along one direction is equal to the contraction in the perpendicular direction. And this is the shearing strain, therefore, and that is equal to 2P into 1 plus sigma by Q. Rigidity modulus of the material of the cube is given by eta equals tangential stress by shearing strain, that is equal to P by theta, that is equal to P divided by theta is 2P into 1 plus sigma whole divided by Q. Rewriting this, we get Q divided by 2 into 1 plus sigma. This is the rigidity modulus. Now, equation 2 implies 2 plus 2 sigma equals Q by N or Q by eta, that is equal to 2 sigma equals Q by eta minus 2, or Q equals, from equation 1, Q equals 3K into 1 minus 2 sigma, where Q is the Young's modulus, K is bulk modulus, and sigma is Poisson's ratio, and Q equals 3K into 1 minus 2 sigma. From equation 1, rewriting we get 1 minus 2 sigma equals Q by 3K, or 2 sigma equals 1 minus Q by 3K. Now, from equations 3 and 4, their LHS being same, we can equate their RHS. Therefore, Q by eta minus 2 equals 1 minus Q by 3K. Or Q by eta plus Q by 3K is equal to 1 plus 2, that is equal to 3. Or Q into 3k plus eta by 3 eta k, that is equal to 3, or q equals 9 eta k divided by 3k plus eta. This is the expression for the Young's modulus. Now equation 1 implies q equals 3k into 1 minus 2 sigma, and equation 2 gives q equals 2 eta into 1 plus sigma. Since their RHS being the same, we are equating their RHS. We get 3k into 1 minus 2 sigma, that is equal to 2 eta into 1 plus sigma. Expanding, we get 3k minus 6k sigma equals 2 eta plus 2 eta sigma. Rewriting, we get, I bring this term to the RHS and this to the LHS. We get 2 eta sigma plus 6k sigma, that is equal to 3k minus 2 eta. I took sigma common over here, therefore sigma becomes equal to 3k minus 2 eta whole divided by 2 eta plus 6k. This is the expression for the Poisson's ratio. Now the limiting values of sigma. From equation 1 and 2, 3k into 1 minus 2 sigma equals 2 sigma into 1 plus 2 eta into 1 plus sigma. The values of eta and k are always positive. These values are always positive. If sigma is to be positive, both sides of equation 7 should be positive. Or otherwise, the RHS of equation 7 is already positive. The LHS becomes positive if 2 sigma is less than 1 or sigma is less than half. If sigma is to be negative, the LHS of 7 becomes positive, for which the RHS is to be positive, sigma should be greater than minus 1. Hence, the theoretical limiting values of sigma are minus 1 and half. These are the limiting values of Poisson's ratio sigma. The practical value of sigma is found to be between 0.2 and 0.4. The negative value of this sigma indicates that the material will expand laterally when it is stretched longitudinally. The negative value of sigma indicates when the material is expanded in one direction, its dimension will be decreasing in the opposite direction. No material behaves in this way. In practice, sigma will be greater than 0 and less than half. So these are the values of Poisson's ratio. Thanking you.